Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Hello. It's really fantastic to have you back with us for this discussion. I was actually, I was staring at my bookshelf this morning. Well, I say bookshelf.
I've seen it's more of a...
Right. It's a chaotic pile of paper and half-read journals. But I was looking at this mess and just thinking about rules. As a species, we are just so obsessed with them.
Oh, absolutely. We crave patterns.
We really do. We want to know that A leads to B and that the socks go in the top drawer and the heavy winter coats go in the closet. We need that order.
Well, it's a survival mechanism, really. I mean, if our ancestors couldn't recognize the pattern of, say, rustling grass, usually equals predator.
Right. Run away.
Exactly. We wouldn't be sitting here recording this analysis right now if they hadn't found order in the noise. We are completely hardwired for it.
But the funny thing is, we don't just apply that to the savannah or our closets. We project that exact same desire for order onto the cosmos itself.
We want the universe to be tidy.
Yes. For the longest time, we looked up at the night sky and just assumed there was this cosmic building code, like a set of architectural blueprints that every single star system had to follow.
And to be fair, for a while, looking at our own neighborhood, it seemed like a pretty rock-solid argument.
Because the solar system is surprisingly neat.
It really is. It's easy to assume your own backyard is the standard for the entire neighborhood. And if you look at the solar system, it's astonishingly tidy. It's almost clockwork.
You have a very specific layout. So let's actually dismantle that solar system standard before we completely blow it up later in the show.
Good idea.
When you look at the sun and its 8 planets, and sorry, Pluto, we're still not counting you today, but you see 2 very distinct neighborhoods.
Right. It's essentially a tale of 2 zones. In the inner zone, huddled really close to the sun, you have the terrestrial planets.
Mercury, Venus, Earth, Mars.
Exactly. These are the rocks. They're relatively small, they're dense, they're rich in iron and silicates. They're solid worlds.
I always think of them as the heavy metal band of the solar system.
That's actually not a bad way to look at it. But then you cross a boundary. In astronomy, we call this the frost line, or the snow line.
And this is a super crucial concept for what we're talking about today.
It is. This line is the specific distance from the star where the temperature drops enough for volatile compounds to freeze.
Things like water, ammonia, methane.
Yes. They condense into solid ice grains. Inside that line, it's too hot. Water is vapor. But outside that line, water is essentially a solid rock.
Ice behaves like rock out there.
Exactly. And that boundary marks the beginning of the outer zone. This is the realm of the gas giants and the ice giants.
Jupiter, Saturn, Uranus, Neptune.
Right. And these worlds are just massive. They dominate the outer system with thick, swirling atmospheres that are thousands of miles deep.
So the cosmic building code that we wrote based on this observation was pretty simple. Rocks on the inside, gas giants on the outside.
That was the rule.
And this wasn't just an aesthetic choice by early astronomers, right?
Oh.
There is hard physics backing this up.
Oh, there's very solid physics behind it. It all comes down to the behavior of the protoplanetary disk.
The swirling saucer of gas and dust that surrounds a baby star.
Right. When a system is forming, the area close to the star is an absolute inferno. The intense radiation and the heat, they prevent those really light gases like hydrogen and helium from sticking around.
They just get blasted away.
Exactly.
Yeah.
Blown away by stellar winds.
Yeah.
And more importantly, the seeds of the planets in that inner zone are made only of rock and metal, which are actually pretty rare materials in the grand scheme of the universe.
So you have a scarcity of building materials close to the star.
You do.
Fair.
You can only build a small planet because there just isn't enough rock to build a big one. And because it's so hot, even if you did grab some gas, you can't hold on to a thick atmosphere.
It just boils off.
It gets stripped away. It's like trying to hold a snowball in a sauna. It's just not going to last.
Whereas if we travel past the frost line,
It is a totally different story. Out there, it's freezing. Ices are solid. So suddenly there is a massive abundance of building material because ice is incredibly common.
so you can build a much bigger core.
Exactly. You can build a solid core that is 10, maybe 15 times the mass of Earth. And once a planetary core gets that heavy, its gravity becomes so strong that it starts sucking up all the gas in the neighborhood.
It hits a tipping point.
Right. It becomes a runaway process. It vacuums up the hydrogen and helium, and boom, you get a Jupiter.
So the logic is completely sound. Heat creates rocks. Cold creates giants. We had the observation, we had the physics, and we basically wrote the law.
And for decades, pretty much all planetary formation models were built entirely around this architecture. We just assumed that if we looked at other stars, we would see the exact same thing.
Which perfectly brings us to our topic today. Because the universe, as it turns out, really enjoys mocking our laws.
It does have a habit of doing that.
Just when we thought we had the blueprint figured out, we found a system that is essentially looking at our physics textbooks and laughing.
It's definitely a curveball. A massive one.
So today we are exploring a distant planetary system that is breaking all the rules. A system that is making astronomers question the very timeline of how worlds are actually born.
And the system we're talking about is known as LHS 1903.
LHS 1903.
Right. And I really want to be clear about the stakes here for everyone listening. This isn't just about finding a weird planet.
Right, because we find weird planets all the time.
We do. Diamond planets, lava worlds. But this is about finding a planet that, according to our standard models of accretion and migration, physically shouldn't exist where it does.
It's an impossible object based on the rules we just laid out.
It is an absolute enigma. And solving it requires us to completely abandon the idea that planetary systems are these static structures. We have to start treating them as dynamic, evolving timelines.
I love that distinction. Space isn't just a place, it's a sequence of events. So here is the roadmap for our discussion today. We're going to transport ourselves to LHS 1903 just to set the scene. Then we are going to look at the impossible planet that was discovered by this massive international team.
The twist in the story.
Right. And then we're going to spend some serious time on the detective work, because the researchers tried really, really hard to prove this planet was just a mistake in the data.
They did everything they could to kill their own anomaly.
And finally, we will unpack the radical new theory of inside-out formation that they propose to explain it.
It is a classic scientific mystery.
Let's start with the setting. Take us to LHS 1903. If I am looking out the window of my spaceship, what kind of star am I looking at?
You are looking at a red dwarf star. Now, we often hear red dwarf and think small, dim, maybe a bit boring.
Just a little glowing ember.
Right. But these are actually the most common stars in the entire galaxy. They're called M dwarfs. LHS 1903 is smaller than our sun, it's cooler than our sun, and it is much, much redder.
So if it's cooler than the Goldilocks zone,
The habitable zone, where water can be liquid, yes.
that zone would be much closer in than it is around our sun.
Much closer. The entire scale of the system is sort of shrunken down. The planets are huddled closer to the fire, so to speak.
Huh.
But M dwarfs are also tricky. They can be very active, flaring violently. And that complicates the whole atmosphere stripping mechanic we talked about earlier.
Because if it's throwing out massive flares, it's going to blast away atmospheres even more aggressively.
Exactly. Now, this system has been under surveillance for a while. This isn't a brand new star we just noticed.
Right. The team observing it has been at it for a bit. It's co-led by researchers from McMaster University and the University of Warwick.
Yes. And they've been doing incredible work using a combination of ground-based telescopes and space-based data to really understand the architecture of this specific system.
And initially, this system looked like it was following the rules. It was a good, law-abiding star system.
It really seemed to be. Before this recent discovery, we knew of 3 planets orbiting LHS 1903. Let's call them the original trio.
Okay, the original trio.
And their layout was incredibly comforting to astronomers because it perfectly matched the pattern we expected.
Walk us through that inventory. What did the map look like originally?
Well, closest to the star, you have the inner planet. And as expected, it is a rocky world. It's bathed in radiation. It's incredibly hot. It has a high density. It fits that inner zone profile perfectly.
Check. Just like Mercury or Earth.
Yeah.
A rock near the star.
Exactly. Then you move a little further out. You find Planet 2 and Planet 3. And these are not rocks. The team characterized them as miniature Neptunes.
Let's define that really quick. When we say mini Neptune, we aren't talking about a water world, are we?
Not necessarily water, no. We are talking about planets that have a solid core, likely rock and ice, but they are enveloped in a very thick hydrogen and helium envelope.
So they are gas-dominated.
Very much so.
Oh.
They have low densities. You couldn't land a spaceship on them. You would just sink through the cloud layers until the atmospheric pressure crushed you.
Okay, so look at the map so far. Inner zone is a rock. Middle zone is gas. That sounds extremely familiar.
It is the standard blueprint. You move away from the star, the temperature drops, and the planets get gassier. If the survey had just stopped right there, LHS 1903 would have been just another data point confirming the standard model.
It would just be in a textbook as example A of normal planetary formation.
It really would. Nothing to see here, folks. The physics works.
But science is rarely that kind to us. The team didn't stop looking.
They did not. And this is where the instrumentation really becomes the hero of the story. They utilized the European Space Agency's Cheops satellite.
I really want to pause on Cheops because it's not as famous as Hubble or the James Webb Space Telescope, but for this specific kind of detective work, it is an absolute beast.
It is a total marvel of engineering. Cheops stands for Characterizing Exoplanet Satellite. And note the word characterizing.
Right, it's not a discovery tool primarily.
Exactly. It isn't a hunter like the Kepler telescope was, scanning thousands of stars just looking for random blips. Cheops is a sniper. It stares at stars we already know have planets.
Why dedicate a whole satellite to stare at something we've already found?
Precision. It's all about precision. Cheops uses ultra-high precision transit photometry.
Meaning it watches the shadow.
Right. It measures the tiny dip in light as a planet crosses the face of the star. But it does this with such extreme sensitivity that it can determine the exact radius of a planet to a refined degree that ground-based telescopes simply cannot match.
Because ground telescopes have to look through Earth's messy atmosphere.
Exactly. The atmosphere blurs the starlight. Cheops is above all that.
So it's the difference between seeing a blurry shadow pass by a frosted window versus seeing the crisp silhouette of a specific person and knowing exactly what kind of hat they're wearing.
That is a very fair analogy. And this precision is vital because it allows us to calculate density properly. If you know the exact size from the transit shadow, and you know the mass from other methods, like how much the planet's gravity makes the star wobble.
The radial velocity method.
Exactly. You combine size and mass, and you get density. And density tells you if you are looking at a dense rock or a flicky cloud.
So Cheops is just staring at LHS 1903, refining the data on those 3 known planets, just doing its job. And then...
A blip.
A blip.
A fourth signal in the data. After years of characterization efforts, the light curve revealed a completely new fourth world. It has been designated LHS 1903e.
Planet E. Okay, so now knowing what we know about the standard model, and knowing that we already have rocks on the inside and gas on the outside in this system, where is this new planet located?
That is the multi-million-dollar question. LHS 1903 is the farthest planet from the star. It orbits way outside the path of those 2 mini-Neptunes.
Okay, so we are in the deep outer zone. We are well past the frost line. We are in the freezer.
Correct. We are out in the region where the protoplanetary disk should have been cool, calm, and incredibly rich in volatiles and gas.
So by every law of physics we discussed earlier, Planet E should be a gas giant.
Absolutely.
It should be another mini-Neptune, or maybe even a full Neptune. It should have scooped up all that cold gas.
That is the overwhelming expectation. But when the team crunched the density numbers from the Cheops data, the result was completely unambiguous. LHS 1903e is not a gas giant.
Don't tell me.
It is a rocky planet.
That makes no sense.
It makes absolutely zero sense under the core accretion model.
Let's visualize this planetary sandwich. We have the star, then a rock, then gas, then more gas, and then way out in the cold, another rock.
Exactly. It's like walking out into the ocean, getting past the crashing breakers, swimming way out into the deep water, and suddenly you just step on dry land.
Wow. Why is this physically impossible, though? I mean, obviously, rocks can exist anywhere, right? Asteroids are rocks out in the cold. Pluto is mostly rock and ice. Why can't a full planet be a rock out there?
It's all about mass and gravity. To be a planet of this size, and Planet E is what we call a super-Earth, so it's substantial, you have to form a core that is roughly 5 to 10 times the mass of Earth.
Okay.
And once a protoplanet reaches that specific mass threshold, its gravity becomes too strong. It automatically starts holding on to hydrogen and helium gas.
It becomes that vacuum cleaner we talked about.
Yes. And out in that orbit, during formation, there should have been plenty of gas to vacuum up. So if it formed there and it got big enough to be a super-Earth, it must have an atmosphere. Physics demands it.
But it doesn't.
It doesn't. The fact that it is naked, just a bare rock, implies that something stopped the vacuum cleaner from working. Or there was simply nothing to vacuum.
This is the massive friction point for astronomers. You have a huge core sitting in what should be a gas-rich environment, but it has no gas. It's like finding a sponge at the bottom of a swimming pool that is completely bone dry.
That is the perfect image for it. And that dry sponge forced the research team to play detective. They couldn't just publish a paper and say, well, physics is broken.
Right, they'd be laughed out of the room.
They had to rule out every other conceivable explanation first. They had to prove this wasn't just a misinterpretation of normal events.
So let's enter the CSI exoplanet phase of our discussion. When you find an anomaly like this, you have to assume you were just missing a piece of the history. And the first assumption in astronomy is usually that something violent happened.
Violence is definitely a common theme in planetary history. So the first theory the team tested was the giant impact hypothesis.
Right. The idea that planet Ease actually was a gas giant once, it followed the rules, it had a thick atmosphere, and then wham!
Exactly. The theory posits that the planet formed correctly as a mini Neptune. But then, a massive object, perhaps a rogue planetary embryo or a huge asteroid, struck it with unbelievable energy.
Enough energy to just blast the atmosphere away into space.
Right, leaving only the dense, rocky core behind.
Yeah. Now, this sounds highly plausible to me. We know impacts happen all the time. Our own moon formed from a Mars-sized object hitting Earth. Uranus is tipped completely on its side, probably because of a massive impact. Why couldn't that be the answer here?
It comes down to the energy budget. Stripping an entire planetary atmosphere, especially one held by the gravity of a super-Earth, requires a cataclysmic amount of energy.
It's not just a little fender bender.
No, we aren't talking about a dinosaur killer asteroid. We are talking about a direct collision with another planet-sized object traveling at immense speed.
A planetary demolition derby.
Yes, and when you run the numerical simulations of that kind of collision, you immediately run into major problems. First is just the probability.
It's too rare.
A collision that is precise enough to cleanly strip the gas away, but somehow leave the rocky core completely intact and in a stable orbit, is vanishingly rare. Usually you just shatter the planet entirely.
Okay, what's the second problem?
Where is the debris? A collision of that magnitude creates a massive debris disk. Millions of fragments, dust, shattered crust, and all that dust would absorb starlight and glow brightly in the infrared spectrum.
Oh, and we don't see any glowing dust.
The system is completely clean. Furthermore, the current orbit of planet E is relatively circular and stable. A massive atmosphere-destroying impact usually perturbs the orbit significantly. It makes it highly elliptical or wildly inclined compared to the other planets.
So the forensic evidence just isn't there.
It's not. The blood spatter pattern, to keep the CSI analogy going, just didn't match a murder scene.
Okay, so suspect number 1, the giant impact, is released for lack of evidence. What about suspect number 2? Because this one honestly seems the most likely to me. Migration.
Planetary migration. This is really the darling of modern exoplanet science. We know for a fact that planets move. We are fairly certain Jupiter migrated in our own solar system early on.
Right. So the theory here is simple. Planet E wasn't born in the outer zone. It was born in the inner zone, the rock factory, right where it belongs. And then, through gravitational pinball, it got kicked out to the suburbs.
It's the drifting rock hypothesis. It formed inside the frost line as a normal rocky planet and then migrated outward over millions of years. This would explain perfectly why it is rocky. It was baked in the oven and then simply moved to the freezer.
So why did the team rule this out? It sounds like the perfect alibi.
It fails the gravitational fingerprint test. You see, when planets migrate, they do not slide silently through the night. They interact gravitationally with absolutely everything they pass.
Because they are heavy. They drag things around.
Exactly. They warp space. Specifically, in a compact system like LHS 1903, where you already have 3 other planets tightly packed together, a migration of that magnitude would force the planets into what we call mean motion resonances.
Let's break that down for the listener. What does a resonance look like?
It means their orbital periods would lock into mathematical integer ratios. For every 2 times the outer planet orbits the star, the inner one orbits exactly 3 times, a 3-to-2 resonance, or a 2-to-1 resonance.
Like gears in a clock.
Exactly like gears, or like pushing a kid on a swing. You time the pushes perfectly so the energy builds up in a rhythm. We see this all over the place. The moons of Jupiter are in resonance. The planets in the TRAPPIST-1 system are in a beautiful resonant chain. It is the absolute hallmark of migration.
It's the scar tissue left behind by planets moving through the system.
Precisely. But when the researchers performed the deep orbital analysis on LHS 1903, they found that the planets are not in these resonant chains.
They aren't locked together.
Not at all. Their orbits are essentially random relative to each other. There's no mathematical harmony there.
So the total lack of resonance essentially proves they didn't push each other around.
It strongly implies that the current architecture we see is the birth architecture. These planets formed roughly exactly where they are sitting right now.
Yeah.
They didn't shuffle the deck later on.
This is incredibly frustrating. It didn't get hit by anything. It didn't move from the inner zone.
Which leaves us with the impossible truth. It formed in situ. A naked, rocky world formed directly in the gas zone.
We are right back to the dry sponge in the swimming pool. How do you possibly explain that without breaking physics?
This brings us to the new theory proposed by the researchers.
Yeah.
And honestly, it is a beautiful piece of lateral thinking. They realized that for decades we were looking at the problem spatially. We were obsessed with where the planets were.
Right, inner zone versus outer zone.
But to solve this, we needed to look at it temporally.
It's not about space, it's about time.
Correct. The theory is called inside-out planet formation, or sequential formation.
Okay, explain the mechanism here. How does adding time to the equations solve the gas problem?
Well, we have to abandon the core assumption that all planets in a given system start growing at the exact same moment. The standard model basically assumes a concurrent formation. It's a race where the starting gun fires and every seed everywhere starts building at once.
Like putting a giant tray of cookies into the oven all at the same time. They all bake together.
Right. Instead, the inside-out model asks us to imagine a buffet line. The food on this buffet is the gas and dust of the protoplanetary disk.
Okay, I like this.
But this buffet has a very strict time limit. The kitchen is actively closing.
Because the star is the kitchen manager and it wants everyone out.
Exactly. The central star is actively blowing the gas away with its solar wind and photoevaporation. The disk is slowly dying from the moment it forms. Now, in this sequential model, the inner planet forms first. It grabs the rock available in the hot zone right next to the star.
Okay, so planet 1 is done. It ate first.
Then, a bit later, the process ripples outward and triggers the formation of the next zone. The mini Neptunes start forming. And at this point in time, the buffet is still well stocked. There's plenty of gas swirling around.
So they grow their solid cores and they successfully turn on their vacuums and suck up that thick hydrogen envelope.
They get their fill completely. They become gas-rich mini Neptunes.
But the clock is still ticking.
The clock is ticking constantly. The disk is dissipating. By the time the wave of planetary formation finally reaches the outer edge, where planet E is trying to be born, millions of years have passed.
And the buffet is empty.
The trays are completely scrubbed clean. The gas is largely gone. It was either eaten by the mini Neptunes or it was just blown out into deep space by the star.
So planet E starts to form. It manages to build a massive rocky core using the solid ice and dust pebbles that are still drifting around.
It builds a core easily big enough to hold an atmosphere.
But when it flips the switch and turns on its vacuum cleaner?
Nothing happens.
Wow.
There's literally no gas left to accrete. It becomes a failed giant. It is a massive rocky core that absolutely would have been a Neptune if it had just shown up to the party a million years earlier.
That is just fascinating. It's a rocky planet not because of where it is in the system, but because of when it is in the timeline.
Exactly. It is essentially a fossil of the exact moment the protoplanetary disk died. Its composition perfectly captures the moment the system ran out of fuel.
This concept of sequential timing really changes how we have to view the ingredients of a world. It means you can't just look at an orbit through a telescope and instantly know what the planet is made of based on a simple chart.
You can't. You have to know the history. You have to know the temporal flow of the system. The researchers suggest that the final composition of a planet is actually a record of the local conditions at the exact time of its final assembly.
Local conditions at the time of final assembly? That honestly sounds like a manufacturing disclaimer on the back of a TV.
It effectively is. It tells us that planet formation is a chaotic, highly time-dependent process. It is not a static blueprint printed out at the beginning of time. It is a movie, and the ending of that movie depends entirely on how fast the early scenes play out.
So LHS 1903E is a naked rock simply because it was late. It was the ultimate straggler.
He was the late bloomer in a dying system. It missed the gas window.
This realization must be sending massive ripples through the astronomical community. Because if this inside-out sequential process can happen at LHS 1903, surely it is happening elsewhere.
That is the big sweeping implication of this paper. We have to ask ourselves a very uncomfortable question. Is this system a unicorn, just a bizarre freak occurrence? Or is it actually a very common pattern that we simply haven't had the technology to see until right now?
I suspect from your tone, you lean toward the latter.
I absolutely do. The data point argument is very strong here. You see, for years, our detection methods were inherently biased. We found hot Jupiters because they are huge and they orbit closely, making massive transits and huge gravitational wobbles.
We found what was loud and easy to find.
Exactly. We built our standard models based on the loudest things in the sky and our own backyard. Now that we have ultra-precise tools like CHEOPS, and soon we'll have the Roman Space Telescope, we are finally seeing the subtle, quiet systems.
We are seeing the true diversity of the galaxy.
We are realizing that the solar system standard might just be one specific item on a very, very long menu. You can have systems with hot Jupiters. You can have systems with migrating Neptunes crashing through the inner system.
And you can have inside-out systems where the outer worlds are starved rocks.
It's all about timing and local conditions. The galaxy is far more creative than our old models gave it credit for. The lead researchers basically echoed this sentiment, pointing out how remarkable it is to witness a rocky world confidently existing right where theory says it absolutely shouldn't be.
It reminds me a bit of the Fermi paradox in a weird way. We keep asking, where is everyone? Assuming that life absolutely needs an Earth-like system with an Earth-like timeline to exist. But if planetary systems are this wildly diverse, maybe the conditions for life are also more diverse. Or perhaps much rarer than we thought.
It certainly complicates things. If you need a very specific architecture to protect a habitable planet, like maybe you need a Jupiter sitting further out to catch all the incoming asteroids and shield the inner planets.
Right, the Jupiter shield theory.
Yes, and if that specific architecture is rare, then maybe calm Earths are rare. But on the flip side, maybe rocky worlds are far more common in the safe, quiet outer zones than we ever dared to hope.
That's a really hopeful thought. Think about a rocky super-Earth way out in the outer zone. If it had enough internal heat from radioactive decay or tidal forces, could it have a subsurface ocean?
It's completely possible. Look at Enceladus and Europa, right here in our own system. They are icy moons with deep, vast liquid water oceans under the ice. A massive super-Earth in that position could potentially harbor incredibly deep liquid water, protected from the vacuum by a thick crust of ice.
It opens up a totally new class of potential real estate for astrobiologists to think about.
It really forces us to stop being carbon chauvinists, or I guess solar system chauvinists, about how planets are supposed to look. We are not the gold standard. We are just one random outcome of a chaotic, time-sensitive process.
So looking forward, we have this brilliant new theory of sequential formation. How do we prove it? What is the next logical step for this research team to confirm this wasn't just a lucky guess?
The immediate next step is atmospheric characterization. And the tool for that is the James Webb Space Telescope.
JWST. What exactly would Webb be looking for in a system like this? It can't look at the rock because there's no atmosphere to sniff.
Correct. But it can look at the mini Neptunes in the middle. If the inside-out sequential theory is right, the chemical abundance ratios in their atmospheres should tell a story. Specifically, we look at the amount of carbon versus the amount of oxygen.
Why those two elements?
Because, as a protoplanetary disk evaporates over time, the ratio of gas to solid dust changes. Carbon and oxygen freeze at different temperatures and different times. So the ratio of those elements floating in the gas changes as the disk gets older.
Oh, I see. So the chemical signature basically acts like a timestamp.
Exactly. The chemistry gets baked into the atmosphere of the planet when it forms. If Webb can analyze the light passing through the air of those two mini Neptunes and find a specific gradient in those ratios that implies they formed at different times.
That would be the smoking gun.
It would be definitive proof for sequential formation. We would literally be reading the timeline of a dead disk in the clouds of a living planet.
That is just incredible. We are using telescopes to do temporal archaeology on a solar system 100 light years away.
It really is the golden age of exoplanetary science.
Yeah.
We are finally moving from stamp collecting, where we just find planets and put them on a list, to actually understanding their life stories.
Well, this analysis has certainly blown my mind today. We started with such a simple, comforting rule. Rocks inside, gas outside.
A very tidy rule.
And we ended up with a starved, naked super-Earth sitting out in the freezing dark telling us a story about the agonizing death of its birth cloud.
And reminding us once again that the universe is far more dynamic and messy than our textbooks would like to admit.
I think the biggest takeaway for me is just the element of time. We look up at the night sky and it looks so perfectly still and eternal. But it's really all just a freeze frame of a violent, constantly shifting history.
Chaos and order, just dancing together across millions of years. That is the true nature of the cosmos.
Thank you so much for breaking all this down. It really makes you wonder, if our tidy little system is actually the weird one, what does normal actually look like out there? What other bizarre, rule-breaking architectures are hiding in the dark, just waiting for a satellite to spot them?
And importantly, how many anomalies have we simply missed or ignored in the past because we were only looking for patterns that matched our own home?
That is a fascinating thought to end on. Keep looking up, keep questioning the rules you think are permanent, and we will see you in the next discussion. Goodbye.